How's it going, everyone? Hope you're all having a good day so far. Does anyone have any questions before we get started? Okay. So today we're going to start Chapter 5, which is talking about the topic of probability. Everything that we did in Chapters 1, 2, and 3 was working with, how to get samples, how to make charts out of our data, how to, calculate statistics from our data, and how to do some of the basic analysis of our data. So in Chapter 5, we're moving completely past that into the realm of probability. This will actually be the topic for Chapter 5 and 6. So our next test will be over these two chapters, 5 and 6, which, again, probability is the primary topic here. There are some ancillary topics to go along with that, but this is the foundation, basically. Alright. So we start off again with definitions, as we tend to always do. Probability is the likelihood of a random event occurring. Okay. So when we say a random event, we mean that's some event where the outcome is not guaranteed. The outcome may have some level of expectation, and this is kind of in the realm of what we call classical probability, and I'll go into this a little bit more in a moment. But the idea is that, if we flip a coin, there's really only two options, and we expect each of them to have equal probability of occurring. Okay? And so, in that case, we realize that, when there's only like two options, we can easily calculate the probability of each outcome. Even if we're just rolling a die or a pair of dice, we can. There's already established probabilities as far as outcomes go. We don't have to think about it. But there's other things where, if you think about let's say a basketball player shooting a free throw. In that case, there's no guarantee what's going to happen. You know, we kind of know how well it's going to go on average, but that's really based on past experience versus any kind of expectation for the future. So there's really different kinds of probability that we want to look at. Things that are based on a limited number of outcomes with a reasonable expectation of each, and others where the outcome is unknown, but based on historical evidence we have an idea about how likely something would be to happen. Okay, so that's the idea of classical probability versus what we call empirical probability. Okay. So, classical probability I missed a letter there, sorry. Classical probability means the outcomes are known and based on, well, let me say that again. Outcomes are equally likely to occur. That's probably the best way of saying it. Outcomes are equally likely to occur regardless of outside influences. Well, not regardless, but under normal circumstances, I guess. Basically, when we roll a pair of dice, we know there's only if we roll 2 dice and we add up the sum on the die, we know it's going to be any number between 2 and 12, and some numbers are more likely to occur than others based on the different combinations that are possible on the dice. If we flip a coin, we know it's either heads or tails. If we have numbers 1 through 10 in a hat, and they're unfolded slips of paper, and we choose one at random, we know they're equally likely to be chosen. So in that scenario, that's what we call classical probability, and we can easily predict the probability of different events that could happen there, and different combinations of events that could happen there because of that. But the other type is empirical probability, and this is probability that's based on what has happened in the past, or what is known to be true already from past experience. And this is what we see in a lot of sports statistics. It's all based on empirical probability. The rate at which a basketball player shoots a free throw successfully, the rate at which a baseball player successfully reaches base every at bat, that kind of thing. So those are all considered empirical because it really that average that we get is a reflection of what has happened either in the short past or maybe their entire playing history. Usually we're more concerned with what has happened like in the current season of that sport because it reflects a more recent trend because things change over time. People get better, people get worse, people get older, different things are affecting outcomes. So In that sense, we tend to look at it on a limited basis, although we could also look at their lifetime of work and compare those two. And those probabilities are all based on experience, based on what's happened previously. But yeah, but we can also use the same thing outside of sports. It's not just a sports thing. We have empirical probability. On our test, we remember, which I haven't graded. I'm sorry about that. I haven't finished grading, let me say. On our test, we had a question about voting participation, and again, that's based on past statistics. It doesn't mean it's going to be the same this year. We won't necessarily have the same numbers this year. Likely will be different, but is it significantly different? We don't know for sure yet. I mean, we'll have to wait and see what happens. Hopefully, we have higher participation, and I think there's a bigger push than usual for voter participation. But how effective that is, we don't know. So, anyway, well, that's kind of our basics of, you know, the different types of probability that we'll work with. Now, one thing that we have to understand, and this is talking about classical probability in particular right now, where outcomes are equally likely to occur. You know, we know that when you flip a coin, you know, it's 50% chance that lands on heads and 50% chance that lands on tails. That's the probability, actually. Okay? But that doesn't mean if we flip a coin 10 times, it's going to be exactly 5 and 5. 5 heads, 5 tails. More than likely, when we flip a coin 10 times, we might see some variation there. There's a lot of different possibilities. I mean, we might see 4 and 6 of one or the other. Maybe 3 and 7. Although the further we get from 5 and 5, the less likely those are to occur. It's very unlikely that we flip a coin 10 times and it lands on tails 10 times in a row. Extremely unlikely. But that doesn't mean it couldn't happen at the same time. But if we flip a coin 100 times, we'd be closer to 50-50. Probably. Again, there could be a very unusual events taking place, but overall, this is, you know, what we expect to be true in the long run is that as we continue flipping a coin, the closer the proportion should get to be 50% for each outcome, because there's only 2 outcomes and they have equal opportunity to, or equal likelihood to occur. Okay, and the same thing is, you know, occurs if you roll a single die that has 6 sides. We know that there's a 1 in 6 chance it lands on 1, 1 in 6 chance it lands on 2, 3, 4, 5, and 6. And so those are all considered classical probability because we know exactly at what rate things should happen, although in experience we may see some different results. But what happens is, over a large number of trials, over a large number of repetitions of this experiment, like if we flip a coin 1,000 times, the proportion, I mean the probability that we witness should approach what is called the classical probability, which is that it should be 50% for each. Okay. So if we flip a coin 1,000 times and we end up with a difference of more than 10 or 20 between the 2 outcomes, very unlikely for that to happen. Okay. That would be an interesting experiment, but not one that would be fun to undertake, it turns out. Alright, so the law of large numbers says that, let me write this down on the sheet of paper here. So as the number of repetitions of a, let's call it a probability experiment. Probability experiment increases, the closer the observed probability gets to the expected probability. Okay. So we have the concept of observed probability and then expected probability. We have certain, based on what has happened previously, or if it's classical probability, we know what to expect. But then what we observe through actual experimentation, the more times we repeat that, the closer it should get to the actual expected probability. Okay? All right. Now, I mentioned probability experiment here. Let's define that a little bit further. Again, we're getting into more terminology now. A probability experiment is probably a good way of saying that is any process where the outcome is randomly determined. Not randomly determined. Yeah, it would have to be random. Maybe not truly random. The outcome is, maybe the book is a better word. The book uses the word uncertain. That might be a better way of saying it. It's not necessarily random, but it's uncertain. So the outcome is uncertain. Yeah, I do like that a lot better. Yeah. Okay. Each repetition of the experiment is called a trial. And all of the different outcomes that are possible are referred to as the sample space. Okay. So I've underlined our, terminology words. And finally, an event An event is any collection of outcomes from a probability experiment. Okay. So there we have a lot of our different terminology expressed. So if our let's see, so let's say our probability experiment is that we want to flip a coin 50 times. And we want to know the number of times that tails was landed on. Okay. In that case, the number of trials is 50. That's the number of times the coin flipping has been repeated. The sample space is the different outcomes that are possible, which is heads and tails. And the event there that we're interested in is the number of tails that were landed on. Okay. Now, an event may have a single outcome, or it may be multiple outcomes. It just depends on what we're expressing. For instance, if we're rolling dice, we may say one event would be, what's the probability that we roll a pair of dice and the sum that shows on the dice is 7? Well, that would be an event, that the sum is equal to 7. Or you may have another event where the sum is equal to 2, 11, or 12. That is multiple different outcomes, but it's all considered one event. Well, we would call that more of a compound event rather than a simple event, but I'm not going to get caught up in that terminology. It's still just an event. Okay. So we can say, okay, what's the probability that we roll a pair of dice and the sum is odd, or the sum is even? And those contain multiple different outcomes. Okay, and so there's a lot of different things that we could ask there and have it be an event. Okay, it's not just one thing that we could look at, it's any combination of things from the sample space. Okay. Let's look at the rules of probability. So we're going to let E be an event, and then P, parentheses E, we'll call this the probability of event E. So that's a bit of our notation that we use there. So P, parentheses E, is the probability of the event in the parentheses, in this case, event E. Okay. So for 1, the probability of an event probability of an event will always be a number between 0 and 1. And we say that's inclusive because it could be equal to 0 and equal to 1, or equal to 1, or anything in between. So when we say something is inclusive, it includes those numbers themselves. Okay. And the second part here is the sum of the probabilities of the individual outcomes will always be 1. Okay. Basically, when we look at the possible outcomes from a probability event, or from a probability experiment, sorry, the individual outcomes, their probability should always add up to 1, because that represents 100% of the different outcomes. So if it doesn't equal 100%, that means there's some other outcome that we left out for whatever reason that we've missed. Okay? Or we just have an improper probability distribution. That's what the book tends to ask us. We'll look at some of those when we get to it. So the probability of each event is between 0 and 1, and the sum of all the probabilities of individual outcomes will always equal 1. One of the things that we we've already used quite a few formulas, so it's not going to be terribly different in this chapter than the last one. We'll do a little bit more by hand here than we did in the previous chapters as far as calculation goes, but the calculation will be relatively straightforward, adding and subtracting for the most part, occasionally some multiplication or division, but it's all arithmetic based. It's not like algebra or anything like that. Alright. Sorry, that's just a lot of lecture today. It's not a lot of interaction. First section of any new material tends to be like that, just info dump of definitions and concepts, so I apologize if it's not as interesting. Let's look at some actual examples just to do something different. A coin is flipped 3 times. Determine the sample space of outcomes and their probabilities. So, we're using a standard coin, so we know the expectation is that it's a 50% chance that the coin lands on heads and a 50% chance that the coin lands on tails, which incidentally adds up to 100%. That's what we're saying in that last thing with the rules of probability, is that the sum of the probabilities for the different outcomes must equal 1 or 100% if we're using, depending on whether we're using decimal or percentages. We could use fractions, but fractions are not great in comparing to each other, because if they don't have a common denominator, it's not easy to compare fractions. So we tend to prefer to use decimals or percentages in our whenever we write down our answers here, just because they're easy to compare to each other. And it's not terribly difficult to convert from decimal to percent and vice versa. The coin is flipped 3 times and determine the sample space of outcomes and their probabilities. For this, when there's only 2 possible outcomes for flipping a coin, it's one method we can use to determine this is to use what's called a tree diagram. And the concept of a tree diagram is that at the beginning we have our first trial, that's where you flip the coin once and it may land on heads or tails. Now, on our second trial, regardless of whether we got heads or tails the first time, we know it's still equally likely that it lands on heads or tails the second time. So our second trial, if we got heads on the first toss of the coin, we still have 2 equally likely outcomes, heads and tails, on the second trial. And that's true for both. Okay. So even if we got tails first, we still have heads and tails as a possibility. So each time we repeat a trial, we branch off from the previous result. So if it landed on heads, then it has a chance of being heads or tails from there. If the first one landed on tails, then it still has a chance of being heads or tails from there. And the same is true for our third trial when we flip the coin again. And I'm going to get in trouble with the amount of space I'm using here. So this will be a little bit squashed together. Okay. Now, we know that flipping a coin results in a probability of 50% chance landing on heads and 50% chance of landing on tails. Because it is what we call a classical probability, we know exactly what the outcomes are, and they're equally likely to occur. So 0.5 chance of occurring, 0.5. So 0.5 it lands on heads, and 0.5 it lands on tails. On our second toss of the coin, even though we land on heads, that does not influence whether it lands on heads or tails the next toss of the coin. So 0.5 and 0.5. And that repeats all the way down. Each time we toss the coin again, it's still an equal chance of 0.5 or 50% of each outcome occurring again. Okay. Now, let's make another column over here. This is our sample space at the end. And what we do is we'll follow the different branches down. Like if we go the top branch each way, lands on heads again, and lands on heads a third time. It's heads 3 times in a row. It could be heads, then tails. So this particular series of branches is heads, heads, tails. Next it could be heads, then tails, and then heads. And then heads, tails, and tails. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And all 3 tails. Okay. So that's our sample space of possible outcomes. And each one of these is a unique ordering as far as how the coins may land. Okay. Now the way that we figure out the probability of each of these is by multiplying this the outcomes all the way down. So for when it landed on 3 heads, so it's 0.5 for the first one, 0.5 for the second one, and 0.5 for the third one. So we multiply those together, and that gives us 0.125. Okay. And because on every branch is 0.5, it's actually the same for each one of these. And if we add those together, it does add up to 1. Because 0.125 8 times is exactly equal to 1. Okay. Now, let's say we have an unfair coin where it lands on tails 75% of the time and heads 25% of the time. For whatever reason, the coin has been weighted or has some material removed on one side, and it alters the flight. I don't know if we can actually do that. I know it's possible with dice, but not necessarily with coins. But let's pretend at least. So maybe it turns out that there's a 25% chance it lands on heads and 75% chance it lands on tails. Well, we can go through and change these numbers, 0.25 for heads and 0.75 for tails, and we would still have the same outcomes in the sample space, but their probabilities would be entirely different based on that. As for heads 3 times, it would be 0.25, 0.25, 0.25. We get a very different number. Okay. And tails 3 times would be 0.75, 0.75, 0.75. Get a very different number. And each combination in between would have the same thing taking place. So the tree diagram is useful in that it allows us to compare things that either have the same probability, or if they have different probability, we can still use it. The downside to the tree diagram is that it's very time consuming for something that even has just 2 outcomes like we do here. Okay. Ultimately, because these are equally likely, the tree diagram is completely redundant. And if we have 3 outcomes, we know it's going to be 0.5 for each, so it's automatically 0.125 for everything. So we didn't really need a tree diagram to figure out those probabilities. But I think it helps us at least see the outcomes that are possible. Okay. Now, there's some different questions we could ask here. We could ask, okay, what's the probability it lands on heads 3 times in a row? We know that probability is 0.125. We could say, what's the probability that heads is landed on twice? Well, there's 1, 2, 3 outcomes where it lands on heads twice. Heads, heads, tails, heads, tails, heads, and tails, heads, heads. And we would add together those probabilities, which would make it 0.375. So, let's see, we said probability of heads 3 times. So it's 0.125. And then we said the probability of heads exactly twice. And this would be heads, heads, tails, heads, tails, heads, and tails, heads, heads, would be 0.125 plus 0.125 plus 0.125, which is 0.375. Okay? So there's different events that we could calculate the probability for. In this case, we're just adding the numbers together if there are multiple event or multiple outcomes possible, which is generally what we do. Okay. So that's one type of probability question that we could have. Let's look at a different type. Let's go back to our, this is another example I mentioned earlier, and that is we have a hat that contains the numbers 1 through 10 folded on slips of paper inside. Now, let's look at how we define probability, or define the calculation of probability. Probability we say is the n of e divided by n of s. Now, n of e is the number of ways an event is successful. This is the probability of e specifically. I'm sorry. N of e is the number of ways event e is successful. And n of s is the number of total possible outcomes. And we call it n, indicating the number of whatever's in the parentheses. So if we're referring to event e, n of e is the number of ways event e is successful. S refers to the sample space, actually, so basically it's the number of elements in the sample space, which is the number of possible outcomes. What is the probability of selecting a 2 if we draw a number at random from this hat? What's the probability we pull one slip of paper and it has the number 2 written inside? So we think about, okay, how many ways could we be successful? I mean, how many of these numbers have the number 2 written on them? Well, exactly 1. What are our possible outcomes? Well, there's 10 possible numbers here. So there's 1, 2 out of 10 possible numbers, so our probability is 1 out of 10. Okay. This is now more calculation based, but it's still classical probability because we anticipate each of those 10 numbers being equally likely to be drawn if we pick one at random. Okay. What is the probability that we select a 7? And again, we don't want to leave it as a fraction, we'll just change it to a decimal, so 0.1. Does the probability change whether we select a 2 or a 7? Anyone have a idea there? No? No, it doesn't change. I think that's what you're responding to, Haley. Yeah, the probability doesn't change whether we're selecting a 2 or a 7. So it's 1 out of 10, correct. Now, we could make a different event. What's the probability of selecting an even number? Well, we think about how many ways could that happen out of the the total number of possibilities. So what's the probability of getting an even number if we pick one number at random? Again, we're thinking of how many ways can we pick an even number, how many outcomes would be successful, divided by the total number of possible outcomes. And we know whatever happens, we have 10 outcomes here. So the question is, how many even numbers are in the hat to begin with? Five out of 10, or 50%, right? One of the things you'll notice is I tend to use decimal instead of percentage. And that's because percentages are fine because we're able to convey meaning with them, and we're able to compare them easily. The reason I would prefer decimals, at least personally, is that if we have to use this result in any other formula, we want it to be a decimal because percentages don't play nice with other numbers that are not percentages, it turns out. So, but decimals do, and that's the main reason. So I would prefer decimal, but if you want to write percent, that's fine. But I would just say no on fractions. We don't want to deal with fractions anyway. So in this case, fractions are kind of a mean to an end. We establish what the different numbers are, and then we actually calculate it from there. And it won't be that we always have a nice number 10. It might be that we have 1 out of 7. And in that case, the fraction is more accurate. But again, the decimal allows us to compare numbers better. Anyway, what is the probability we select a multiple of 3? So we think of how many numbers between 1 and 10 are multiples of 3. Three out of 10, good. So 0.3. And again, a multiple of 3, that would be 3, 6, or 9. Okay? Because 3 times 1 is 3, 3 times 2 is 6, and 3 times 3 is 9. So those 3 numbers are multiples of 3. What is the probability we select an 11? 0. There aren't any 11s in the hat. Therefore, this is what's called an impossible event. Okay. Essentially, it will never happen. At least the way it's set up. I mean, if we do pull an 11 out of this hat, then someone's got some explaining to do. Alright. How are we doing on time? We're doing alright. Okay, I covered that. Covered that. Okay, we're doing all right. Let's see if I can get this properly situated. Looking at number 8 here in the book. Sorry. Verify that the following is a probability model. If the model represents the colors of M&Ms in a bag of milk chocolate M&Ms, explain what the model implies. So, to be a proper probability model, we said that all the numbers have to be between 0 and 1, including 0 and 1 themselves. And the sum of the probabilities must equal 1. So first of all, is this a valid probability model? Well, we can see all the individual values are between 0 and 1, including 0 and 1. And we can easily see the sum here is equal to 1. So yes, it's a valid probability model. What does this particular model imply? Well, it implies that every M&M in the bag that we found was yellow, which would be very unusual, but well, almost impossible, actually, I would say. Unless it was like a special edition bag or something, or you just went to the M&M store in I remember in Las Vegas there was an M&M store there where you can basically buy whatever you wanted, so you could get a bag of yellow M&Ms there if you wanted to. So, anyway, but yeah, so that would be a valid probability distribution or model. Technically, we haven't talked about distribution yet. All right, and then number 10 here. Let me zoom in. Why is this not a probability model? Well, I kind of gave it away there because you can see the answer in my book. The first thing we look at is, again, are all the numbers between 0 and 1? And the answer is yes, here all of the numbers are between 0 and 1. But the other issue is, to be a valid probability model, the sum of the probabilities must equal 1. And that, in fact, is what's wrong here. As you can see, it says in the book, the sum of the probabilities is not 1. If we add these together, it ends up equal to 1.2, which means either the probabilities have been miscalculated or we have some wrong data somewhere besides that. And so, again, it's the same thing when we were talking about the rules of probability before. That's what we're looking for here. Are all the probabilities between 0 and 1, and do they add up to 1 collectively? And that's what we're checking for. All right. Oh. Let's zoom back out. Okay. Now we said empirical probability is based on past results. Okay, just to remind us. So let's say, for example, we flip a coin 100 times, and it lands on tails 80 times. Empirically, what is the probability that it lands on tails the next time we toss the coin? What do you think that would be? Logically, we know there's a 50% chance it lands on heads or tails, or 0.5. But, at the same time, as scientists, if we witness this happen where we flip a coin 100 times and it lands on tails 80 times, it could mean that there is some flaw in the coin. And based on what we've witnessed, what is the observed probability or the empirical probability? Well, in this case, if we're basing it on our observations, we take the previous results. In this case, that when we flip the coin 100 times and it lands on tails 80 times, we take the total number of trials, which is 100. That's our denominator, and then the number of successes on the numerator. So 80 out of 100. So we would say that there's a 0.8 probability, or 80% probability, that this particular coin lands on tails the next time we toss it. Realistically, if we know that this is a fair coin, we know that the probability should be 50%, or 0.5. But based on what we've seen, based on the evidence that's given, this particular coin, if it lands 80 times on tails out of 100, if it is a fair coin, this is a complete outlier. Almost an impossible event, impossible outcome, almost an impossible outcome, if this is a fair coin. So, but based on what we've witnessed, 80% of the time, it's going to land on tails. Okay? And so our observation there means it would be that perhaps this really is not a fair coin, for whatever reason. Okay? So, but realistically, if it is a fair coin, oh, sorry about that. Probability of tails is 50 out of 100 or 0.5. So this is observed, and this is the classical probability. And observed is the same thing as empirical. Sorry about that. So there's two perspectives there. From what we've witnessed, there's an 80% chance it lands on tails. But from what we know, fundamentally, as statisticians, it should be 50%. So there's one or two things. Either it's not a fair coin, or it's just a complete outlier of a series of trials where it actually had an 80 to 20 ratio instead of 50-50. Okay, let's see. Suppose my my sock drawer. We'll talk about my sock drawer more later when we get to multiplication rule, but I'll just introduce some basics here. This is of course, a theoretical sock drawer, but the numbers have been changed to make calculations easier. It turns out, I don't know. I may have 100 socks. I don't really go in and count. I don't think I have 100 socks though. Anyway, suppose my sock drawer contains 100 individual socks. We'll say that my socks are not very interesting. Let's go with that. So we'll go with 60 white socks. Maybe we have 27 black socks because I've lost one somewhere in the washing machine or dryer. And then what's left? 13 gray socks. We've actually lost 3 of those, it turns out. Okay. That adds up to 100, I'm pretty sure. So what is the probability that we select a white sock at random? So we select one sock at random. What's the probability that it's white? Now, we're supposing that each of the 100 socks in this drawer is equally likely to be selected. So, it would be 60 out of 100, right? Because we have 60 white socks in the drawer out of 100 total. So there's a 0.6 probability of selecting a white sock. Now, what is probably a better question here, what is the probability of getting a pair of white socks? Because that's certainly what I am interested in every morning. Not from 100, but whatever number of socks I have. Less than that, I assume. Because I should take, it's much less than 2 months before I have to wash. Anyway. That particular question, though, of choosing two socks back to back, that's the one that we are not quite ready to talk about. We will talk about in an upcoming section. It turns out when we pick one sock and then we pick a second sock, the probability for the second sock is different because there's one less sock in the drawer. And you can probably already get an idea of what I'm talking about, but then the way we calculate that, we have to be careful. So there's two events there, and we have to we'll eventually learn how these two events interact with each other. So okay, what is the probability of getting a white or black sock? So this particular morning where I want either a white or a black sock, apparently I'm just not feeling the gray that day. So, for whatever reason. What do you think we would do with the numbers in that scenario? Yeah, we know this. It's 60 out of 100 for white and 27 out of 100 for black, but what if we combine those together? If we want white or black, it could be any of those how many socks? $87, good. There's not a whole lot of events we can look at here. It's either just one color or a combination of colors, one of which we're interested in. And again, in this case, we're only choosing one sock. We're not choosing a pair, so it's probably not as interesting a problem as it could be. But we're still looking at the basics of probability in this first section. So if we want one or the other, then we just have to add the possible outcomes together where they're successful out of the total number of outcomes. It's still that same n of s divided by n of e divided by n of s rule that we talked about before with empirical or observed probabilities. It's just based on each sock being equally likely to be chosen. Which is classical. Yeah, this is actually classical. But it could also be observed. Let's see, what else do we need to do here? Oh, yes. This one we will need a calculator for. I'll get one out. Alright. Let's see, a bit of a glare on there. That's probably a little bit better. In a national survey conducted by the Centers for Disease Control to determine college students' health risk behaviors, college students were asked, how often do you wear a seatbelt when driving a car? The frequencies appear in the following table. So they've already given us the frequency distribution. So we have never, which is 118, rarely, 249, sometimes 345, most of the time 716, and always 3093. So we want to A, construct a probability model for seatbelt use by a driver. So the idea here is that we're given just the raw data, and they want us to create the probability model where we list out the different responses But instead of giving the frequency, we give the actual probability of that as we observe from the study. Now, in this case, the probability is essentially the same as the relative frequency that we studied in the last set of material, chapter 2, I guess, and also in 3 to an extent. And mainly as chapter 2, I think we saw the relative frequency. So that's kind of what we have to do here. We have to, calculate how likely each of these is to occur, which for the never responses, that's 118 people out of however many are in the entire study. And we repeat that for each of the individual outcomes. So the probability, excuse me, and the probability is exactly like the relative frequency in studies like this, where we just we're studying the data and we're looking at a table that represents the responses. Okay. Turn that light back on. All right. So, am I still zoomed in? There we go. This is on page 259, number 36. So we have response, and we have frequency, and we're going to create a third column, which is probability, which turns out to be the same as the relative frequency in these type problems. So we have never, rarely, sometimes, most of the time, and always. Let's see, 118, 249, 345, 716, 3093. Okay, so first thing we'll want to do is add up the frequencies so we can get the total frequency. And I get 4521. Okay. So what's our probability of never? Or how would we calculate the probability that a college student never uses their seatbelt when driving? For the sake of time, we know that we're just going to take our 118 and divide that by 4525. sorry, 4521, and that comes out to be 0.026. I'm just going to go to 3 decimal places on these. This is 0.055. 0.076. 0.158. And 0.684. Now if we add these together, it actually comes out to 0.999. Doesn't equal 1. Well, why do you think that happened? Well, the main reason is that when we're calculating each of these values, it doesn't come out to be an exact decimal, and so each of these numbers is rounded to the 3rd decimal place. Okay? So because of rounding, it won't necessarily be, it won't necessarily be equal to 1, but it should still be very close to 1. So if this came up as 0.998, or 1.002, that's a reasonable range to be able to account for rounding error. Now, if this came out to be 0.979, that would be a little more suspicious if we were further off than like fractions of a percent. So it's expected when we're rounding these values that it may not come out to be exactly 1, but it should still be very close. Okay. Now, an unusual event, this is the last thing we'll cover. An unusual event is less than 5% chance of occurring. At least that's how the book defines it. I feel like it's kind of a nebulous concept, but generally speaking, we'll say an event is unusual if it has a less than 5% chance of occurring. And so, the other question that I asked here, part B, is it unusual for a college student to never wear a seatbelt when driving? And the answer is yes, because this is actually 2.6% smaller than 5%. Okay. Very quickly, let me give you some homework problems, which will be on page 257. We'll start with 7 and 9. $15. 23 through 26. Go ahead and include 27 also. And 30. And 37. And that's it. So look over those problems. Sorry for going a little bit late. I wanted to finish up that section today. And again, keep working on the project that's still due next Wednesday. Or Tuesday, sorry. Y'all have a good rest of the day, and I'll talk to y'all on Thursday. Bye.